the like silicate in the glass or something. I mean, that's why we can have clear glass windows and it doesn't leak all of the heat out of our houses. And that's also how greenhouses work, right? So you have light coming in, it goes down, it heats up the inside of the greenhouse, and then it can't leave out of the windows.
Right. Good point. Silicon says Cliff.
Yeah. It's a silicone in the glass from Cliff.
Cool.
Oh.
We got a lot of folks from California on here, Humboldt and Community Observatory right up the road, all the way out to Florida. It's great to see you all. Welcome.
Hey.
Yes.
Well, I also made the my cat keeps trying to eat the microphone, so I put it up now. Another reason I was a little discombobulated. Also had to move the desktop up because he discovered that the two fans that are on top of the desktop feel really good for him to sit on. It's not good at all for the computer.
But
he was not happy.
Oh, wow. Baton Rouge. Wonderful.
Yeah, near LIGO.
Yeah, that was a cool webinar. We had one a while back on the LIGO detectors. Very cool new image of the black hole, by the way. That made my whole astronomy week.
I think it'll be really cool once, I think that Webb in particular probably could do some work in conjunction with the LIGO to find some of those sources. And, I think it's great how you get all these observatories working together.
That is the future. Multi-wavelength, multi-messenger astronomy.
Amazing.
Well, we're at the top of the hour. Let's go ahead and get started. So hello, everyone, and welcome to the May NASA Night Sky Network member webinar. We're hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to welcome back our guest speaker, Dr. Kelly Lepo from the Space Telescope Science Institute. Welcome to everyone joining us on the YouTube live stream. We're very happy to have you with us. These webinars are monthly events for members of the NASA Night Sky Network. And for more information about the NASA Night Sky Network and the Astronomical Society of the Pacific, we'll put some links in the chat in just a moment. Before we introduce Kelly, here's Dave Prosper with just a couple of announcements.
Hi, all. Apologies if I'm a bit sleepy at the moment. I just returned from, let's see here, sorry. I'm gonna switch the gallery around a bit. There we go. Sorry. So I just returned from a lovely time at NCRAL in Wisconsin this past weekend, and it was a really great event. Still kind of recovering a bit from the travel, but it was really good meeting so many of you. And we'll be at Alcon 2022 in Albuquerque this July as well, and hope to see many of you there too. And I really love New Mexico. It's where I started like really seriously stargazing. So I'm very, very happy to return. We also have a couple of announcements for some partners. The Astronomy Ambassadors in Chile program is now accepting applications. It's a great program. If you've done any of the big astronomy toolkit stuff, you know what it's all about. So they are now accepting your applications now through the end of this month, May 31st, 2002. I could talk about it some more, but Vivian, would you want to say a word or two? You're the expert.
Oh, I cannot recommend it enough. You get to go and visit a lot of the amazing large telescopes in Chile, up to Alma and the Atacama Desert, see the new Vera Rubin telescope. There are so many amazing things happening in Chile, and I think getting a chance to see those is a once-in-a-lifetime opportunity. I really encourage you to apply, and they love to have amateur astronomers join, and astrophotographers, or anyone who's doing outreach as well. So I encourage you to do that. You're welcome to ping me with any questions.
Thank you, Viv. Awesome. It's great. The other announcement we have is NASA's Astrophoto Challenges are open for this summer. And so this edition, it's already started and runs through July 31st. And everyone's, of course, invited to participate. You can create your own amazing images of the Karina Nebula using NASA data, or get your own data from remote telescopes. You can find out more in our article or on the official site. I'm going to put the links in the chat in a second. Also, one last item is that we have a special webinar series coming up for this summer. It's more of a virtual meetup. The Summer Social Series is going to be where we seek expert advice for issues related to amateur astronomers. And those experts are you, all of you out there. So the format's more of a two-way meeting than a webinar like this format. We hope it to be pretty lively, fun, pretty informal. June's theme will be what are your outreach essentials? Which means what are your can't miss activities, equipment, supplies, emergency items, and so on. What do you pack when you go out to show people the stars or tell people about space? Just so you know, we won't be recording or streaming these events to YouTube. This is just an NSN members only thing, and it'll be via Zoom. The information will be in the newsletter and all that good stuff. So keep your eyes out for that. And I'm going to put the link in the Zoom chat for the first registration too. And that's it from me. Brian, back to you.
All right, thanks, Dave. And also, those of you that happen to go to the Oregon Star Party in late July, you can see me there. And I'll also be speaking about the Eclipse Ambassadors program. It's never too early to start thinking about planning your eclipse events for 2023 and 2024. Vivian, do you want to say something really quickly about the Eclipse Ambassadors?
Stay tuned. There's going to be applications opening up in July. So we'll give you lots more information. Stay tuned for that.
All right, thanks. For those of you on Zoom, you can find both the chat window and the Q&A window at the bottom edge of your Zoom window on your desktop. Please feel free to greet each other in the chat window or to let us know if you're having any technical difficulties. You can also send us an email at nightskyinfo@astrosociety.org. If you have a question for Kelly, please put it in the Q&A window. That way we don't lose it. And if you do happen to chat, make sure you go down to that little button at the bottom and select everyone so that we can all see your message. And so I'm going to go ahead and start the supplemental recording here. So again, welcome to the May webinar of the NASA Night Sky Network. This month, we welcome Dr. Kelly Lepo to our webinar. Dr. Kelly Lepo is an education and outreach scientist at the Space Telescope Science Institute, where she works to support outreach efforts for the upcoming Webb Space Telescope. She has a PhD in astronomy and astrophysics from the University of Toronto. She's made numerous local and national media appearances to talk about everything from the 2012 Mayan Apocalypse to the super blue blood moon. That's a mouthful. She has also served as the coordinator of the McGill Space Institute, designed undergraduate teaching labs, taught physics at Gonzaga University, and helped build the Large Hadron Collider at CERN. And so she's, got lots of experience here, and she's going to tell us all about what we can look forward to with the Webb Space Telescope. So please welcome Dr. Kelly Lepo.
So thank you, Brian, for that lovely introduction. And I think I put super blue blood moon in my bio just to trip up people who have to introduce me. So I'm going to go share my screen here. And there we go. So thank you so much for having me back. I'm really excited to talk to you all about what to expect from the upcoming first year of science from the James Webb Space Telescope. Again, my name is Dr. Kelly Lepo. I'm an education and outreach scientist at the Space Telescope Science Institute. STSCI is the home of the science operations of the Hubble Space Telescope and also the science and mission operations of the Webb Space Telescope, which means a couple floors above my office. Right now, there are people in the control room who are planning on sending commands to the Webb telescope, which is it's an exciting place to work. And I am here to share my excitement about the first year of science with Webb with all of you all. So we are going to go to the next slide. There we go. So we're going to nerd out a little bit tonight We're going to talk about the James Webb Space Telescope. We'll talk about launching the telescope, why we want to study infrared light because Webb is an infrared telescope, the cool science that we're going to be able to do with Webb, about the telescope itself, and what we're doing right now to prepare for Webb's first observations. So I don't know what you were doing on Christmas morning of last year. I was in my very fancy pajamas with my family watching NASA's live stream of the launch of the James Webb Space Telescope, NASA's next flagship observatory. Webb launched from the European spaceport near Kourou, French Guiana on December 25th, 2021. It launched on an Ariane 5 rocket, which was the European Space Agency's contribution to the mission. So here we have our last view of the Webb Space Telescope as seen from the rocket fairing on the Ariane 5 rocket. And so I would like everyone right now to wish Webb good luck on its voyage out to L2, its parking spot about 1 million miles away from the sun. So looking at this view of Webb, we can see two things. Number one, it's pretty shiny, which tells us we're looking at the underside of the observatory. And number two, it's pretty compact. So the Webb telescope is actually really, really big. Its Sunshield is the size of a tennis court, and its mirror is the size of a 2-story building. But it was actually, as designed, too big to fit inside of our largest rocket, which means that the designers of Webb designed an incredible folding telescope. And so as Webb left the Earth on its way to its parking spot 1 million miles away from the sun, over the course of about 30 days, the telescope unfolded itself in this deployment sequence, which was very carefully choreographed. This included tensioning and separating the Sunshield layers, unfolding the secondary support structure, which held the secondary mirror in place. That's the little mirror in front of the big mirror, and also unfolding the wings of the primary mirror. And the primary mirror is made up of 18 hexagonal gold-coated segments. How do we talk to Webb? We talk to Webb via the Deep Space Network. So we sent all of these commands to Webb to unfold itself via the Deep Space Network, which is a series of radio telescopes in 3 locations in California, in Spain, and Australia. The round trip, it takes about 5 seconds for light to travel from Earth to L2, and then it takes about 5 seconds for the data from Webb to come back to Earth. So it's 10 seconds round trip. Webb, during science operations, will downlink twice a day and downlink at 28 megabits per second, so we can get 57.2 gigabytes of data down per day. Where is Webb right now? I said it's at L2. So L2 is the second Lagrange point. Lagrange points are these very special points. They're special solutions to what physicists call the 3-body problem, when you have 2 massive objects like the Earth and the sun, and a smaller object like a spacecraft. And at these special points, the gravity from the 2 large objects, the Earth and the sun, balances the orbital motion of that third object. So there are 5 Lagrange points for any system labeled L1 through L5. 5 of these points, of the 5 points, 3 are unstable and 2 are unstable. So the unstable Lagrange points are L1, L2, and L3, and those lie along the line between the 2 massive objects, the Earth and the sun. And spacecraft that orbit at these points need to expend small amounts of propellant for station-keeping maneuvers to keep themselves at these points, because if it's sort of like being on top of a hill, if you nudge something just a little bit, it tends to fall out of that point. L4 and L5 are stable Lagrange points, and those are within the orbit of the Earth and the Earth-Sun system. L4 leads the orbit of Earth and L5 follows. Okay, so Webb is at this special point called L2, but you'll notice both in the diagram that I just showed you and this diagram here that Webb doesn't orbit exactly at L2. It actually orbits around L2, partially because it's an unstable point, so you don't want to nudge it a little bit and have it go flying, but also because if Webb was exactly at L2, the Earth would eclipse the sun, and that would be bad because then we wouldn't have any sunlight on our solar panels, and we need electricity to run our telescope. So Webb does this big halo orbit, bigger than the orbit of the Earth, bigger than the orbit of the moon around the Earth. And why is it so far out? Well, it's because Webb is an infrared telescope and it needs to be very, very cold. And it also needs to have a very stable thermal environment. So it can't orbit around the Earth like Hubble does. It would be too warm and the temperature fluctuations would be too big. Okay, so let's break this down a bit. Let's talk a little bit about infrared light, and then we can understand why Webb has to be so cold. So there are lots of different types of light. We can only see a small fraction of those types of light. The whole range of light that exists is called the electromagnetic spectrum. And infrared light is light that is slightly redder than the light our eyes can see. Why do we study things with infrared light? Well, it's because we can get new information about things by looking with different types of light. So, for example, here we have two images. We have meerkats on the left and a freshwater crocodile on the right, taken with a normal visible light camera. And then we also have a series of two images. We have the meerkats and the freshwater crocodile again, but this time with an infrared camera. And so when you look at these things with infrared eyes, you see more information about these animals. The meerkats are warm-blooded and we see their cute little bellies glowing with infrared light because everything is glowing even if we can't see it with our eyes. The freshwater crocodile, on the other hand, is about the same temperature as the ground, so it's not glowing as brightly. But in general, you and me and the computer I'm talking into and the meerkats and the crocodile and anything that's about room temperature will glow very brightly in infrared light. So again, here we have the electromagnetic spectrum showing all the different types of light there are. The Hubble Space Telescope sees from the blue end, or sorry, the edge of the UV all the way into visible light and a little bit of infrared light. So I'm going to show you a couple infrared images in this presentation, and almost all of them come from this little sliver of infrared light that Hubble is able to see. Webb sees from sort of the orangey red side of visible light all the way into the red and the mid-infrared end of infrared light. The Spitzer Space Telescope sees from the near-infrared, the area of infrared near visible light, all the way into the mid-infrared as well. So why do we want to look at space with infrared eyes? That's partially because the universe is full of dust. And by dust, I mean like dust, like soot and sand particle dust. So here we have a very famous image of a star-forming region, the Eagle Nebula's pillars of creation. And we see these very dark, dusty columns, and we can't see through them because the dust is scattering visible light. If we look at the middle panel, this is another Hubble image, but this time we can see through these dark, dusty columns in infrared light. Infrared light can penetrate dust to see the stars that are forming inside and also the stars that are behind these columns of gas and dust. And then if we move over to the mid-infrared, we see these columns glowing themselves. This is the dust glowing in infrared light. So if you want to study dust or see through dust, infrared is where you want to look, depending on the wavelength. Also, if you want to study the early universe, you have to look in infrared light. So all telescopes are time machines, and that is because light takes time to travel. So the farther back you look, the farther back in time you look. And light that has been traveling for a very long time through the universe to reach us gets stretched out to redder and redder and redder wavelengths, which means that if you look at very distant galaxies, they may have emitted their light at ultraviolet or visible wavelengths, but by the time it gets to it, it has been stretched out so much that we see it as near or mid-infrared light. So if you want to study the very distant things in the universe, you have to look with infrared eyes. Okay, so that's our very brief introduction to infrared astronomy. Let's talk about all of the cool science that Webb is going to be able to do. So we're going to start big, and then we're going to go smaller. So let's start at the very beginning, because that's a very good place to start. And we'll pick up our story shortly after the Big Bang, right when the universe is done with what I like to call its boring period, when the universe was just filled with neutral hydrogen gas. So it was, just gas, no stars, no planets, no galaxies, very boring. And then the gas started to clump together and form the first stars and the first galaxies and the first black holes. And these new baby galaxies started shining very brightly at ultraviolet wavelengths of light. And this ionized the gas around them. So it kicked electrons off the gas around it. And it blew these bubbles. And it ionized the gas. And these bubbles grew and grew until the universe became clear. So the universe changed from an opaque cloud of dust to a mostly clear universe punctuated with stars and galaxies. And this is called the era of reionization. And this is something Webb will study. So why don't I give you a very specific science highlight, a program that's going to study this time. So the Cosmos Webb survey has 200 hours of observing time to study a large patch of sky about 0.6 square degrees, or about the area of 3 full moons. The program will study 500,000 galaxies in near-infrared light, and it'll also simultaneously map a smaller area of about 32,000 galaxies in mid-infrared light. And one of the goals of this program is to study this era of reionization, to look for these bubbles being blown by the first galaxies and figure out where these first pockets of light that are blowing bubbles in this field of neutral hydrogen gas, and map the scale of this and map the time of it. When did this happen in the early universe? Along similar lines, Webb will study some of the first galaxies. So this is a deep field made by Hubble. It's the Goods Field North. And this is done by pointing your space telescope at an otherwise dark patch of sky for a very long period of time and collecting all of the photons that come in to see what shows up. And so almost every single one of these points is a galaxy, which is just completely wild. And I'm highlighting one of these points here. This is the current record holder for furthest thing seen by Hubble. It's a galaxy called GN-Z11, and we're seeing it as it was 13.4 billion years in the past. That's just 400 million years after the Big Bang. So Webb will also find galaxies like this, find some of the very first galaxies to form after the Big Bang. So a program that's going to study this is the CEERS survey. It has about 60 hours of time on the first year of Webb. It's the Cosmic Evolution Early Release Science Survey, and it will take both images and spectra to understand this early phase of the universe. It will observe the extended growth strip, which is shown in the background here, which was observed as part of the Hubble's Candle survey. And the goal of this program is to identify the most distant galaxies in the universe, understand early galaxy mergers and interactions, and find some of the first massive and supermassive black holes in the history of the universe. Another big Webb theme is studying galaxies over time. So it's not just the first galaxies that Webb will observe, it's all galaxies throughout the history of the universe. And Webb will do this by looking at snapshots of different galaxies at different times in the history of the universe. So you remember that first earliest galaxy that Hubble has seen, it was sort of small and red and blobby. And this is a theme. The earliest galaxies don't look anything like the galaxies that we see nearby us, which means that galaxies have changed over time. We see them merging and forming new stars, and their black holes pull in and eat new gas and stars, and they slowly turn from these small red blobs into the giant elliptical and spiral galaxies that we see nearby us. So Webb has a unique perspective on this history of galaxies, which will complement other observations from telescopes like Hubble. So here's a specific example. There is an early release science program which will study 4 pairs of merging galaxies, including NGC 3256, which is pictured here. When galaxies merge, the clashing flows of gas accelerate star formation, and it feeds their central black holes. This also tends to kick up a bunch of dust, which means it's very hard to study the central area of these galaxies because it's shrouded by dust. But remember, Webb's infrared eyes allow us to see through the dust, so we'll be able to see what's happening in the cores of these galaxies. So NGC 3256 is a really cool example of this. So looking at this, you might think, well, this galaxy merger is already finished. But if you look behind the dust, what you see is this actually has 2 different cores. So Webb will be able to study this galaxy in great detail, map the central region, look at where the stars are forming, and understand where these 2 black holes at the center of the galaxy are and how they might influence each other. And this is part of a larger program which has studied luminous infrared galaxies across the electromagnetic spectrum from X-ray to radio light. So along similar lines, another big science theme of Webb is black holes. Webb will study black holes both near and far. I hope you all got to see that really cool picture of Sagittarius A star, the black hole at the center of our own Milky Way galaxy. So Webb won't be able to take an image as sharp as that. It turns out that that picture from the Event Horizon Telescope will take the entire image takes up only a fraction of a pixel of the Webb cameras. So Webb won't be able to see the black hole in any detail, but it can see through the dust that blocks our view of the center of our own galaxy. So we'll be able to study the stars and the gas that orbits our own black hole. Moving out a little bit, Webb will study the black holes in nearby galaxies. In particular, it can study the interactions between the black holes, the massive jets that they blow, and the star formation that happens in those galaxies. And then zooming out even further, Webb will be able to study quasars, which are supermassive black holes in the very early universe, study the interaction between the first black holes and the first galaxies, and maybe help to answer the chicken and egg problem, which came first, galaxies or black holes. So here's one highlight of an object that Webb will study. This is Centaurus A. It's a nearby galaxy, very well studied. It's the result of a galaxy merger that happened between 2 galaxies beginning about 100 million years ago. And we see this warped central feature, which is a remnant of this merger. And you also see this giant elliptical galaxy that was formed. So all of those halos around the outside of the image are part of this galaxy. It's really hard to observe this central supermassive black hole because it's shrouded by this dust layer. So Webb will be able to see through this dust to measure the center of the galaxy. It has this cool spectrograph on board where every pixel of the image becomes a spectrum, and we can use that to map the gas that's orbiting around the central black hole and figure out exactly how much that black hole weighs. So we'll zoom in a bit into our own galaxy, and we will understand how stars in our galaxy and nearby galaxies form, live, and die. So this is another beautiful star forming region in the Karina Nebula. It's nicknamed Mystic Mountain. And on the left, you see a visible light image of this nebula. And again, you see these dark, dusty columns. You can't see through them in visible light, but when you look in infrared light, you can study the stars that are forming inside. Webb will also study normal middle-aged stars and stars at the end of their lifetime, things like planetary nebulas and supernovas. So this is one particular research highlight, and this very nerdily is the thing that I am the most excited about, and it's my talk, so I can add it in here. So we will be able to observe Wolf-Rayet binaries. So Wolf-Rayet stars are these evolved, massive post-main sequence O stars. So the most massive stars at the end of their lifetime, and they have these crazy strong winds where they blow off their entire outer layers and basically are just an exposed helium core. And massive stars tend to form in pairs, actually, or higher order multiples. So a lot of times these evolved stars at the end of their lifetime will have a companion, another massive star with very strong winds. And the winds of these two stars collide. And when they do, they end up forming a lot of dust. And they form these really beautiful spiral patterns as they orbit around each other, which is what we're seeing on this slide. And there's some people who think that this is the origin of all of that dust that we're using Webb to see through, or at least most of it. So if most of the interstellar dust comes from these things, we want to understand them. We want to understand the physics of how this dust is formed, and we want to be able to understand if this dust survives after it's formed. And with Webb's really beautiful sensitivity and sharpness, we'll be able to study this for the first time. And hopefully we'll get some really cool pictures like this. And actually, if you observe these over a few years, you can actually see the spiral changing as the two stars orbit around each other. So I'm excited. I would like a video of that, please and thank you. So we'll go back to star forming regions. It turns out that molecules like to wiggle and jiggle and also absorb light at exactly infrared wavelengths. So if you want to know what your nebula is made out of, infrared is the place that you should look. So here's a specific example of something Webb will do. This is the Orion Bar. It is a ridge-like feature of gas and dust, which is being sculpted by a cluster of massive stars. So you have this cold, dense, dark, gassy area. And then you have a massive star cluster, which is shining ultraviolet light. And what ends up happening is you end up having several different layers of gas. So you have the cold area where most of your gas is in molecules. And then as you get slightly closer to the star cluster, your gas heats up and these molecules tend to disassociate. So you call that the dissociation front. So your molecules break up into atoms. And then if you get even warmer, your atoms start to lose their electrons. So they're ionized. So there's an ionization front. And then as you get even warmer, your gas has lost all of its electrons. So you have this fully ionized gas. And so what Webb is able to do is it's able to take images and spectra, spread out the light, see the patterns that are the chemical fingerprints of these different types of molecules and atoms, and figure out where exactly all these different phases of gas are, and understand the physics of star formation regions in really exquisite detail for the first time. And the Orion Bar is very close to us, so we can see this in detail, and we can apply this detailed study to further star forming regions, which we can't observe as closely, but we can apply our findings to those more distant objects. So another big Webb science theme is planets, including planets in our own solar system. So this is an infrared image of Jupiter taken by the ground-based Gemini North telescope. So Webb will observe planets in our own solar system, everything from Mars outward, because you can't point your several billion-dollar telescope at the sun because you'll fry it and that would be bad. So we can look outward, we can understand the atmosphere of Mars, the clouds on Jupiter, Saturn, Uranus, and Neptune, seasonal weather and climate on these gas giants and the planets and moons, and understand the composition of small bodies such as asteroids and Kuiper belt objects and comets. So, an example. Here is everyone's favorite trans-Newtonian object, Pluto, and its moon, Charon. I like to refer to Pluto as the king of the Kuiper belt. Kuiper belt objects are very cold and faint and icy and rocky, and they glow in infrared light. So we can use spectra from Webb to understand the composition of these objects and the weird surface chemistry that's going on. Webb will observe Pluto and Charon to complement the observations made by the New Horizons mission, which took these beautiful photos we're seeing here. It will observe Eris to understand the kinds of ice on its surface, Sedna to figure out why this little hunk of rock is so red, and Haumea to understand its moons and also its ring system. It's not just planets in our own solar system, though. Webb will study planets around other stars. So this is the star HR 8799, and you see 4 dots orbiting around it, and each one of those dots is a planet. So you can't actually see the star itself. We've placed a disk in front of it called a coronagraph, and this blocks out the bright light of the star so we can see the faint planets orbiting around it. Webb has a coronagraph on board, and it also has very fast imaging capabilities, so it will be able to see fainter planets than any telescope before it. And infrared is also a really great place to look if you want to image planets, because planets tend to be about room temperature and glow very brightly in infrared light, and stars tend to be less bright in infrared light, so there's the best contrast between planet and star. Here's another cool research highlight, and I'm showing this mostly because I'm absolutely fascinated by this ALMA D-Sharp collaboration image of protoplanetary disks. So these are disks around baby stars that are in the process of forming planets. And you see gaps in this disk, and those gaps are probably where planets are forming. So Webb will observe these planet-forming disks, but unlike ALMA, which is a radio or sub-millimeter telescope, which is seeing the outer part of the disks, Webb will look into the inner part of these disks. And again, Webb is very good at looking at molecules like water and carbon monoxide and carbon dioxide and methane and ammonia. And also those different molecules look slightly different compared at different temperatures. So the closer you are to the star, the hotter you are, and you'll have different signatures of those different molecules. So that means that you can make a map of which molecules are where in the inner part of these disks, which tells you a lot about what materials that planets forming in the inner disk have. So if you want to understand the inner part of these star systems, like the Earth forming around the sun, Webb will give us new information to which molecules are there, and if the gas that is around these stars is similar to the interstellar gas that these stars and these planets initially formed out of, or if this composition changes over time. Okay, so fully formed planets, Webb can do another trick, and that is if you have a planet go in front of its star, you can watch the light go through the planet's atmosphere. And the atmosphere will absorb certain wavelengths of light depending on which molecules are in the atmosphere. So this is a simulation of what the Earth would look like to an alien astronomer if we could watch starlight filter through the atmosphere. And we can see the signatures here of different molecules like ozone and carbon dioxide and methane and water. Webb won't be able to take spectra in this detail. Again, this is just a simulation, but it gives you an idea of how you can figure out the composition of a planet that is hundreds to thousands of light years away without ever having to take your spaceship and visit. So one object that is of particular interest to astronomers is the TRAPPIST-1 system. These are 7 rocky Earth-sized worlds that orbit an ultra-cool star called TRAPPIST-1. It's 39 light years away from Earth. 3 of those planets are in the habitable zone, and by habitable zone, I mean somewhere where you can have liquid water. And we will be able to measure the atmospheres of these planets. So we'll be able to tell if these planets have an atmosphere or not. And if they do have an atmosphere, is their atmosphere dominated by water vapor or mostly nitrogen like the Earth, or mostly carbon dioxide like Mars and Venus? We probably aren't going to be able to go in great detail, but we will be able to say something about the bulk composition of these planets and their atmospheres. Okay, so that is all of the science that I have time to talk about tonight. There's lots more that Webb will be able to do. I hope that I was able to give you some highlights. And if I missed your favorite program, I'm sorry. But again, I only have an hour. But let's now shift gears a little bit and talk about the amazing telescope that makes this all possible. So Webb is really a feat of engineering. And the engineering was really driven by these ambitious science goals. Webb has specialized optics to align its mirrors, detectors that can capture and separate light from hundreds of sources at once, and these really sophisticated custom thermal control systems. The engineers who created these technologies made Webb the most sophisticated telescope ever launched into space to do science. And all of this really diligent, years-long process and hard work is really starting to pay off, and I'm getting excited. Okay. So let's talk about one challenge of infrared astronomy that the designers of the telescope had to overcome. So remember how I said that everything is glowing, even if we can't see it with our eyes. So trying to observe infrared with a normal telescope is like trying to observe visible light with a telescope made out of light bulbs. So if your telescope itself is glowing, it's hard to see anything else except for the telescope. So to minimize this at infrared wavelengths, you have to make your telescope very, very, very cold. And so your telescope glows the least amount possible in infrared light. Webb does this 2 different ways. The first way is this multi-layer sunshield. So it's a 5-layer sunshield. It's about the size of a tennis court. And this blocks the light and the heat from the Earth and the sun and the moon. And it enables the observing side of the telescope to be very, very cold. So the side that faces the sun, which has the communications equipment and the solar panel and the star trackers, is something like 260 degrees Fahrenheit or 125 degrees Celsius. The cold side of the telescope on the other side of the sunshield is roughly minus 390 degrees Fahrenheit or minus 235 degrees Celsius. That's a huge temperature difference. For mid-infrared observations, the telescope instruments need to be even colder. So there is a cryocooler, a closed loop system that functions like a fancy refrigerator or air conditioner. And this allows the mid-infrared instrument to be even colder, something like 7 degrees above absolute zero. That's minus 447 degrees Fahrenheit or minus 266 degrees Celsius. Brr. Webb's instruments are located behind the mirror. There are on the cold side of the telescope. There are 3 near-infrared instruments. Those see the type of infrared light that is closest to visible light. Those include the near-infrared spectrograph or NearSpec, the near-infrared camera or NearCam, and the near-infrared imager and slitless spectrograph or NearIS, which is combined with a fine guidance sensor, which helps to point the telescope. And there's also one mid-infrared instrument, MIRI. Another challenge of infrared astronomy is that the redder the wavelength you want to observe, the bigger the mirror you need to maintain the same level of detail. So Hubble observing at visible wavelengths and Webb observing at infrared wavelengths have the same angular resolution of about 0.1 arc seconds. So Hubble and Webb will take pictures that are equally as sharp. And Webb does this because it has a much larger mirror. It's 6.6 meters compared to Hubble's 2.4 meter mirror. And also I'd like to point out on this graphic, we have Spitzer. Spitzer has a 0.85 meter mirror, which means that each one of Webb's 18 hexagonal mirror segments is bigger than Spitzer's mirror. I'd like to show another image here. This is a comparison of Hubble and Webb and a human for scale. And this is just to show how stinking big these two telescopes are. Hubble is about the size of a school bus. Webb is the size of a tennis court with a 2-story mirror stuck on top of it. They're both gigantic. And it's sometimes hard when you're just seeing renderings of these to keep in mind the scale. Enormous. And one other really cool thing that Webb is able to do is spectroscopy. So lots of different space telescopes can take spectra, but Webb is really fundamentally a spectroscopic instrument. If you look at all of the time that Webb is going to spend on the first year of science, about 70% of that is taking spectra. So when you think of space telescopes, you might think of these very pretty Hubble images, and Webb will be able to take those images as well. But also hanging out behind the scenes, doing a lot of cool science, are these spectra. And so this happens when you take light, spread it out by wavelength, and you see these patterns, which are the chemical fingerprints of molecules and atoms. And by looking at these patterns and brightness, we can learn about the composition, temperature, density, and movement of objects in space, which is pretty awesome. So here's an example. This is a Hubble image and spectrum of the Southern Crab Nebula. And we can see from the spectrum that the nebula is made out of oxygen and hydrogen and nitrogen and sulfur. So we can learn about objects vast distances away by spreading out their light and getting even more information than we can from a picture. And lastly, before I move on to what Webb is what we're doing to prepare for the first observations, I'd just like to make a brief mention that Webb is an international partnership, and it has been since the beginning. This map shows the number of researchers across the globe who received time to observe on Webb in its first year. And you can see basically wherever there's a concentration of astronomers, there is a concentration of people who are going to use Webb to do science. And every year after this, Webb will allocate time to scientists who successfully propose for time on the telescope. The Webb Collaboration built the telescope. It was made out of 120 American, European, and Canadian universities, organizations, and companies. You might hear this as NASA's James Webb Space Telescope, and NASA is the lead partner on the telescope, but it's really the world's telescope, built in collaboration with the European Space Agency and the Canadian Space Agency. Okay, so in my remaining time, I'd like to talk about what we are doing right now to prepare for Webb's first observations. When we left off last, Webb had unfurled itself and it had arrived at L2. What's it been doing since then? Well, when Webb was launched, each one of its mirrors were stored for launch, and then they were moved to our best guess of where they would be to be in focus. And this is the first image there. So this is an image of one star with each of the 18 mirrors acting as their own telescope. And so if you wiggle each mirror, you can figure out which dot corresponds to which mirror, which is shown in the image on the right. So all of the mirror segments there are labeled, and you can even see that the wings are pretty close together. So the focus here is better than what we were expecting pre-launch. And just to say that these are all real images from the telescope. These are real photons which have hit Webb's mirror, gone to the detector, and then that data has been beamed back to Earth. So we start off by taking each one of these mirror segments and moving the dots so that they form a hexagon, because hexagons are the bestagons. And then we focus the mirrors, and that's the middle image here. And then we stack all of these dots on top of each other, and that's the end image there. And now all of these mirror segments are working together as one telescope. And if you do a little bit more focusing, so that all of your mirror segments are aligned to less than the wavelength of light you are trying to observe. You get this. This is the image, which is behind me as well, which is showing that the telescope is in focus on the near-infrared camera. And we have a bright star in the center with Webb's characteristic snowflake-shaped diffraction pattern, which will show up on all bright stars. But the bright star in the middle is perhaps not the coolest part. The coolest part is the background, because each one of those points, almost every single one of them, is a galaxy. And if you download this picture and zoom in, and I suggest that you do, some of those little galaxies even have little tiny baby spiral arms, which is both adorable and exciting for the science to come. So why does Webb have an 8-pointed star? It has to do with the shape of the mirror and the shape of the struts. So Webb has a hexagon-shaped mirror. Each one of the 6 points there outlined in yellow corresponds to a corner of the hexagon shape of the mirror. And then also we have a second pattern from the secondary mirror supports. And this is caused by diffraction. That's when light as a wave interacts with material, and it makes these very characteristic patterns. Almost all reflecting telescopes have a diffraction pattern, and the exact number of spikes and the configuration depends on the strat structure of where the secondary mirror is, and also the shape of your mirror. So Hubble and Webb have different diffraction patterns. So that was one bright star. Let's look at a whole bunch of bright stars. This is a second image that NASA released showing a section of the Large Magellanic Cloud, showing that all 4 detectors were perfectly in focus, which is really exciting. And let's zoom in to the mid-infrared instrument on the upper right-hand corner. So this goes to show how much better things look when you have a giant mirror in space. So on the left, we have a Spitzer image of the same region, which is one of Webb's scientific ancestors. It's something that inspired the science behind Webb. And you can see these big blobby stars come into sharp focus when we're looking at it with Webb. And we can see these bright stars in the image and a whole bunch of faint stars in the background, which happens when you have a big light bucket to collect all of your photons, which is exciting. Okay, so what's next? We already had the deployment sequence. So Webb unfolded itself as it traveled to L2 over 30 days. The telescope cooled down to operating temperature. We aligned the mirrors to all 4 of the instruments. So now we're in the science instrument calibration phase. And what this is, we're going through all of the different modes of the telescope. We're turning them on, making sure they're working how we think they're working, and also optimizing them so we get the best science out of the telescope when we're ready to start science. So this goes up to about 180 days after launch, which if you do the math is July-ish. So the best I can tell you is that after this process is over, we'll have the first images and spectra sometime in mid-July. I don't have a better date than that, and NASA is a little hesitant to announce a date because I think they don't want to push it back. So sometime mid-July is the best I can give you, but it's going to be a really spectacular July. I'm very excited. So if you want to follow along with this instrument calibration process, you can go to whereiswebb.com. They have links to the Webb blog, which has all of the latest Webb news from NASA. And also it has this checklist of all the different modes that need to be completed before we can say commissioning and the instrument calibration is complete. So that is all I have for you today. I hope you all are as excited as I am about the exciting science to come, about the early universe, the first galaxies over time, the life and death of stars, and planets both inside and outside of our solar system. Thanks. And I'm happy to answer questions.
Oh, and we've got a lot of really great questions here. So let's see, let's get right to them. And so Blaine asked a question a long time ago, because the Webb must always be shielded from the sun, does that mean that there are large areas of the sky that are not visible at any given time?
So yes, Webb can see, I think it's something like 40% of the sky at any one time. But over the course of a year, Webb can see the entire night sky with the exception of things that are very close to the sun. So you can't point your expensive telescope at the sun, but basically you can see the entire celestial sphere over the course of a year.
All right, and so Philip asked a question, what's the warmest temperature that the NEARC and NERSC can operate at?
I do not know that off the top of my head. I am a scientist, not an engineer. So sorry about that.
Well, we just know that they have to be really, really cold.
Very, very, very cold. Very, very cold. That's my scientific answer.
So Mateo asked a question. You had that one image about the different ones with the glowing dust cloud. Said it looked like the glowing dust cloud outshone the stars behind it. Does changing the wavelength of infrared change the subject of the photo in dust cloud compared to the stars behind it?
Yes. So when you go into mid-infrared wavelengths, stars tend to get less bright. So stars mostly shine at UV visible wavelengths. Some of the fainter stars also shine a little bit in the near infrared, and they sort of tail off as you go into the mid infrared. But the dust starts getting really, really, really bright. So yes, you do end up getting the glowing dust ends up overwhelming things. And you can see that a bit in the mid infrared image that the MIRI alignment image. You can see the glowing dust in the background and also some bright stars.
All right, that kind of leads us, that's next one. Vasuki asks, why is Webb unable to observe in the far infrared like Spitzer did?
Yeah, it's because it wasn't designed to be, and also it's not cold enough to do it. So if you tried to use Webb to observe in the far infrared, you would probably just see the telescope itself. It was only designed to look at mid-infrared light. So it doesn't have the detectors and it doesn't have the cryogens on board to get it cold enough.
And that was one of the reasons that Spitzer had a limited life, is because the cryogenic fluids ran out, basically.
Yep. Yes, and Webb does not have that problem. It has a closed loop cryocooler, so that will basically function indefinitely until something else in the telescope conks out.
All right. So Michael asked, will Webb be able to help identify the location and perhaps the identity of dark matter?
So somewhat, yes. So especially in the early universe, one of the programs is trying to understand the interaction between dark matter and regular matter in the early universe. And so you're looking for tracers of mass, and you're looking for the missing mass. So to some extent, yes, but also Webb has a really pencil beam view of the universe. So if you're trying to do large surveys to understand dark matter on big scales, Webb is not really the best tool to do that. Something like Roman is a better tool, which is an upcoming space telescope also being developed at STSCI, where I work.
All right, we've got a lot of questions, and I apologize, we're not going to be able to get to everyone, but we'll try to get to a few more here. And so Rebecca asked, will the data coming from Webb be shared with the public in some kind of central repository?
Yes. So all of Webb data, after the instrument calibration process is over, all Webb data will go to the MAST archive, which is open to anyone. It's publicly downloadable and open source. And also, so that's just the raw telescope data if you want to play around with that yourself. If you want more polished images, where I work at the Office of Public Outreach also releases images and will continue to do so from the first image release all the way into when science results start coming out. And all of those images are in the public domain. You can do whatever you want with them, remix them, put them on a t-shirt, you can, it's up to you.
And kind of speaking of these the images. Christopher notes he's looking forward to seeing images from Webb. Will there be a color palette like Hubble that we got used to that converts specific frequencies into visible light? And so are we going to see the pretty pictures and kind of like with the Hubble palette that we got used to?
Yes, so there is a lot of thought that's going into the palette that Webb will have. If you've seen Spitzer images, they tend to be like pretty like red, green, blue, because Spitzer only had a limited selection of filters. Webb is more like Hubble. It has lots of different filters, so we can have more interesting colors. So yes, Webb will produce some really pretty, spectacular pictures, or so I have been told. I have not seen any yet.
So Pete asked an interesting question. He said, are there any post-processing to eliminate artifacts, such as if there's any cosmic dust settling, any damage that occurs, and what are the chances of a micrometeorite striking a mirror, and could it continue doing science if one or two of the segments are damaged?
So yes, there will be post-processing. So part of this calibration process right now is understanding the telescope and all its little quirks and all of that, so we can subtract out artifacts and be able to do the best science with it. And so Webb does have an open mirror, and so it is designed to be able to continue doing its science even if there are micrometeorite impacts on the mirror. I like to point out that the McDonald Observatory has a telescope that they're still using that was shot at back in the 80s maybe, but there are bullet holes in a professional observatory's telescope and it still works fine. So Webb can still continue on with impacts from micrometeorites in its mirrors.
Right. So Jeffrey asked a question. He said, did I understand correctly that the mirror segments each form their own image, which are then stacked with the other images electronically? So it's not actually optically taking all of the light and combining it. It's all done digitally.
So right now the telescope, all of the mirror segments are aligned. So basically it does function as one big mirror. And so all of these mirror segments are very carefully adjusted so that it basically functions as a big mirror, and we're not relying on like digital trickery in order to do this any more than any telescope is having light from all sorts of different points getting focused in on the detectors.
All right, so we're going to go for just let's say 2 more questions, and I need to find a really good one. So Bruce asks, what's the expected real lifespan of the Webb telescope?
That is a good question, and I would like to know that myself. So Webb has enough propellant on it to last more than 10 years is the best I've gotten out of NASA. It's probably more than 20 years. So the Ariane 5 injection into L2 was so perfect that it's not the propellant on board that Webb that's going to be the limiting factor on its lifetime. It's going to be something else probably that breaks first, and we don't quite know what it is. Webb was designed to nominally have a 5-year lifespan and optimistically have a 10-year lifespan. It has enough fuel to go a lot longer. We've kept Hubble alive for now 32 years. So there's some very clever telescope operators right now who are trying their best to extend the lifetime of Hubble as long as possible. And I'm sure there will be also operators of the Webb telescope who try to extend its lifetime as long as possible. So we don't know at the moment how long it'll last, hopefully for a really long time.
All right, so John asked a question. I like this one. He's assuming that there's a committee that makes choices as to what Webb looks at. Are there going to be any unofficial forays into non-approved areas, kind of like what was done with Hubble when imaging the famous deep fields? That was not in the original plan, but they did it. And so any plans or any thoughts that there's going to be kind of these other ones to just kind of get the wow factor?
Yeah. So there's a committee of astronomers who are peer reviewers. You apply to have Hubble time or Hubble Webb time, and you decide, you say, I want to observe this for reasons and I need this much time, and they approve your program or not. And there's also a small section of time, it's called director's discretionary time. And so the director of the Space Telescope Science Institute can observe whatever he wants. And the Hubble Deep Field was one program that came out of that. The STSCI director decided to allocate time to this deep field. It wasn't chosen by a panel of scientists. So yes, there is a director's discretionary time on Webb. And right now, our director is coming up with proposals of what to do with this time. And there's also some observations that are happening after the first images to look at some exciting targets, which I think that's all I can say right now. But yes, there's going to be some cool. It's not that you can't like sneak into the control room and tell Webb to point at something. There's still a whole process that happens, but there is a little bit of time that's not committee allocated.
Yeah. And our very last question, I just want to ask you, what are you most excited about? What are you most looking forward to, or what do you anticipate you're going to see that's going to fill you with wonder at what Webb discovers?
Okay, well, so a couple of things. Number one, those spiraling massive Wolf-Rayet stars. I am, for some reason, absolutely obsessed with this, and I want to learn everything about how they produce dust. But also the first galaxies, I want to know what they're like, whether they were made out of the first generation of stars or the second generation of stars, and how blobby were they and what the early universe was like. I think that's going to be really exciting and something that really only Webb can tell us. So I'm looking forward to that as well.
All right. Well, thank you so much. This is really wonderful. That's all for tonight, everyone. Thank you, Kelly, for joining us this evening. And thank you, everyone, for tuning in. You'll be able to find this webinar, and this was a question that a few people had in the chat, along with many others on the Night Sky Network website in the Outreach Resources section and on our YouTube channel. And so, yes, by all means, share those links with people. The YouTube is almost available almost immediately, and it'll be up on the Night Sky Network website within the next couple of days. And you can join us on our next webinar on Tuesday, June 21, when Dr. Elliot Quatert will provide some insights into the decadal survey. Once upon a time, the Webb was on the decadal survey, and they suggested that they made it. And so this is kind of the document that is the guidance for solar system exploration for the next decade, including a mission to Uranus. So, it's exciting. So we're going to get a little insight into that document and what the plans are for the next decade. Also join us on the evening of Tuesday, June 14th, for the first of a series of social events where you, the members of the Night Sky Network, share your ideas and good works with everyone. So keep looking up, and we will see you next month. And so good night, everyone.
Thank you so much, Dr. Lepo. That was amazing.
Thank you.
It's a joy to hear everything that's going on.
It's kind of funny when you showed the picture of Pluto, all of a sudden we had a big debate going on in the
oh, yes, I know. I did that on purpose. I'm glad.
So, well, this is great. And there's so much to look forward to.